These are my study notes on Power Engineering, 4th class, Engineering Materials, Unit 10, Chapter 46. Engineering Materials. Learning Outcome. When you complete this chapter, you will be able to describe the mechanical properties of ferrous and non-ferrous engineering materials, plus the effects and purposes of various alloys. Learning Objectives. Here is what you will be able to do when you complete each objective. 1. Discuss the mechanical properties of materials. 2. Describe the various types of ferrous materials with respect to their mechanical properties. 3. Describe the various types of non-ferrous materials with respect to their mechanical properties. Lecture Outline. Introduction. Mechanical properties of metals, including hardness, the Brinell tester and the Rockwell tester, brittleness, ductility, plasticity, elasticity, malleability, and toughness. Types of engineering materials, including iron, cast iron, wrought iron, steel, carbon steels, and alloy steels. Non-ferrous metals, including copper, aluminum, and white metal. Introduction. The properties of a metal are the characteristics by which it can be accurately identified, or by which its range of usefulness can be determined. Power engineers are concerned with the applications and properties of two main groups of metals, ferrous and non-ferrous. The word ferrous is derived from Latin, meaning iron. Ferrous metals include pure iron as well as alloys of iron. Alloys are metals which are made by combining two or more elements, such as iron and nickel. Alloys are created to result in a metal which has greater strength, resistance to corrosion, or to achieve other properties not possible by a pure non-alloy metal. Non-ferrous metals contain no iron, or only trace amounts. Examples of non-ferrous metals are copper, lead, aluminum, zinc, nickel, antimony, tin, and magnesium. Non-ferrous metals can also be combined into alloys, such as brass, which is copper and zinc, and bronze, typically copper and tin. Serviceability and safety are the ultimate criteria in choosing metals. Knowledge of types, their performance, and preservation are absolutely essential. By knowing to what extent each property exists in a metal, the metal can be used with the assurance that it will meet the requirements for a specific application. Mechanical properties of metals. Hardness. Hardness is the ability to resist wear, abrasion, cutting, and indentation. This may be a property which is uniform throughout the metal, or it may be a surface condition of the metal, such as when the metal is subjected to case hardening. Case hardening is a process which increases the hardness of the exterior face of a metal while leaving the interior at its natural softness. This is often done to allow the metal object to absorb stresses. Increasing hardness throughout would also increase its brittleness. The hardness of a metal is often measured using its resistance to indentation. This may be done by a hardened steel or diamond ball, cone, or pyramid pressed into the metal sample to be tested. Another common test is to strike the sample with the indenter and measure how much the indenter rebounds. A softer metal will experience a greater indentation, absorbing kinetic energy from the indenter, resulting in a smaller rebound. Two common tests to measure hardness are the Brinell and the Rockwell tests. The Brinell test. The Brinell test can be performed on materials which are more coarse structured than the Rockwell test is capable of, and is often used to test the hardness of large metal parts. In the USA and Canada, Brinell tests are typically performed on ferrous metals using a 10 mm carbide ball as the indenter, with a standard force of 3,000 kilograms. Tests on softer, non-ferrous metals are performed with a 5 or 10 mm carbide ball with a pressure of just 500 kilograms. In Europe, Brinell tests are performed with a much wider range of ball sizes and pressures. Test method. The carbide ball indenter is pressed into the metal sample at a pressure of 3,000 kilograms for ferrous metals or 500 kilograms for non-ferrous metals for a dwell time of 10 to 15 seconds. A low-pressure microscope is then used to measure the diameter of the indentation made, and then the surface area of the indentation is calculated from its diameter, or a chart is referenced. The hardness value is calculated with this formula. Brinell hardness number, BHN, equals the load in kilograms over the area of the mark in square millimeters. The Rockwell test. In the Rockwell test, a steel ball or diamond cone is placed on a metal sample under a minor load, typically 10 kilograms. The position of the indenter at this point is set as the 0 mark. A major load, typically a total of 100 kilograms for a steel ball or 150 kilograms for very hard metals being tested with a diamond cone, is then placed onto the indenter for a dwell time. The difference in depth between the indenter while under the minor load to its depth under the major load is measured and used as its hardness value. Readings made with a steel ball are referred to as Rockwell B measurements, whereas readings made with the diamond cone are Rockwell C measurements. Brittleness. Brittleness is a property of a metal which permits no permanent deformation before breaking. Brittle materials generally break instantly, without any intermediary stage of bending. It has a lack of plasticity. An example of a brittle material is cast iron. The opposite of brittleness is ductility and plasticity. Ductility. Ductility is a material's ability to deform under tensile stress. This is often characterized by the material's ability to be stretched into a wire. Malleability, a similar property, is a material's ability to deform under compressive stress. This is often characterized by the material's ability to form a thin sheet by being hammered or rolled. Both of these mechanical properties are aspects of plasticity. Plasticity. A material is said to exhibit plasticity, or to be plastic, if it is very soft and easily deformed. Examples of plastic materials include wax, lead, and babbitt. Plastic materials have very little elasticity. That is, they do not return to their original shape after the deforming force has been removed. Materials with high plasticity are not brittle. Elasticity. Elasticity is the ability of a material to return to its original shape after any force acting on it has been removed. Elasticity is one of the most important properties for power engineers to be concerned with, as pipes, pressure vessels, and valves must return reliably to their original shape and position after being altered slightly from pressures or changes in heat. Materials which are tough and ductile, such as wrought iron, typically have high elasticity. Materials which are hard and brittle, such as cast iron, have very little elasticity. Malleability. Malleability is the property which allows a material to be hammered or rolled into other shapes and sizes. Copper is an example of metal which is very malleable. Brittle materials are not malleable. The malleability of most materials will increase significantly when the material is heated, such as when iron or steel is heated before forging. Toughness. Toughness is the property that determines whether or not a material will break under a sudden impact. This property is also referred to as its impact strength, and impact tests are used to determine the toughness of a material. A common test used to determine toughness is the IZOD impact test, in which a sample is notched, secured at one end, and a swinging pendulum is struck against the other end. The amount of joules expended by the pendulum swing necessary to break the sample is used to determine the material's toughness. Types of ferrous engineering materials. Iron. To produce iron, iron ore is placed in a blast furnace. Coke and limestone are added to the iron ore, and the furnace's contents are heated to melt the pure iron out of the ore. Coke is a fuel, often made from coal, with very few impurities. It also produces carbon monoxide during combustion, which prevents much of the iron from forming into iron oxides. Limestone combines with the impurities in the iron ore to form slag, which floats on top of the molten iron and is removed and discarded. The purified molten iron is then ladled off into molds to cool and form pig iron. Pig iron is very brittle and hard, and not very machinable at cold or hot temperatures, and is virtually useless in any real-world application. For this reason, pig iron is refined further into two classes of materials, steel and cast iron. Cast iron. Cast iron is produced by melting pig iron together with scrap iron in a cupola furnace, which is similar to a small blast furnace. The resulting molten iron contains 2 to 4% carbon. White cast iron. If most of the carbon is combined chemically with the iron, performed by rapidly cooling it within molds, white cast iron is produced. White cast iron is very hard and brittle, and is used for machinery parts which are subjected to excessive wear, such as crusher jaws and grinding mill balls and liners. Gray cast iron. If the molten iron is cooled slowly, it causes the carbon to dissociate from the iron and form into graphite. This mechanically combined product, as opposed to being chemically combined, as in the white cast iron, is known as gray cast iron. Gray cast iron is softer, with good compressive strength, and is widely used for machinery bases and supports. Malleable cast iron. If the molten metal is annealed, a process of heating and cooling at a controlled rate, malleable cast iron is produced. This form of cast iron has increased toughness and ductility, and is used for some farming implements, automobile parts, pipe fittings, and tools. Wrought iron. Wrought iron is produced by a process known as puddling, by melting pig iron and allowing the carbon and other impurities to oxidize while it melts, which is then removed. The remaining iron forms a plastic mass, which is formed into a ball by the use of a puddling bar. The ball is then removed from the furnace and squeezed and rolled to remove most of the slag. The result is wrought iron. Wrought iron is very ductile and resistant to corrosion. At one time, it was used extensively for boiler tubes, piping, and bolts. However, steel has largely replaced wrought iron for these purposes. Steel. Steels are alloys of iron and carbon containing less than 2% carbon. If the carbon content is greater than 2%, then the alloy is cast iron. Steels are divided into plain carbon and alloy steels. Plain carbon steels are alloys of iron and carbon only. Approximately 90% of the steel manufactured in North America is produced by the open hearth method, with most of the remainder produced by the electric furnace method. The open hearth furnace is charged with scrap iron, pig iron, and ore, and the heat is supplied by the combustion of gas or oil with preheated air. The very hot gases pass from the furnace through a brickwork checker chamber at one end of the furnace, while the air for combustion enters through another brickwork checker chamber at the other end of the furnace. Every 15 minutes, the gas and air flows are reversed, with the air being heated as it passes through the checker chamber, which in the previous 15 minutes had been exposed to the hot gases. As the charge in the furnace is heated and melted, the carbon content is reduced to the proper point by oxidation, and in this way carbon steel is formed. If alloy steel is desired, then the required alloying materials are added to the molten carbon steel. Special high alloy steel is frequently produced in electric furnaces, where the heat is furnished by electrical arcs. Carbon steels. Carbon steels are grouped according to their carbon content, from low, medium, high, and very high carbon. Hardness, strength, and often brittleness increase with increasing carbon content. Impurities such as phosphorus and sulfur will lower the ductility, malleability, and welding qualities of steel. High and very high carbon steels respond well to heat treatments. Most of these materials may, in the annealed state, be readily machined. Alloy steels. Alloy steel is steel that is alloyed with a variety of elements in total amounts between 1% and 50% by weight to alter its mechanical properties. Some of the alloying elements combine with the carbon to form compounds, Other elements do not form compounds, but remain in solution in the iron. In solution means that the alloy and carbon elements do not combine chemically with each other, but are held suspended as crystals in the ferrite. The main advantages of alloy steels are the ability to respond to heat treatment, improved corrosion resistance, improved properties at high and low temperatures, and combination of high strength with good ductility. Most of the alloy steels may be welded, provided the carbon content is within welding range. Generally, these steels require heating before, during, and after welding in order to avoid residual stress. An example of an alloy steel is specification SA-335-P22, which is a chrome molybdenum steel used for high temperature steam piping. This material is suitable for severe service because its high creep strength and resistance to oxidation and corrosion at high temperatures, above 500 Celsius. Creep is slow, permanent stretching of a material under stress at high temperatures. Some of the more important elements which are added to steel to produce alloy steel, with their effects on the properties of the steel, are as follows. Nickel. Nickel is a tough, silvery element of about the same density as copper. It has excellent resistance to corrosion and oxidation, even at high temperatures. It improves toughness and prevents brittleness at low temperatures. Nickel steels are especially suitable for the case hardening process for such applications as roller bearings and gears. These steels provide strong, tough cases that are resistant to wear and fatigue. Chromium. Chromium resists oxidation caused by hot gases, maintains high strength at elevated temperatures, and increases hardness and abrasion resistance. When chromium is present in amounts in excess of 4%, corrosion resistance is greatly increased. With a minimum of 12% chromium, the steel is stainless steel. Molybdenum. Molybdenum increases hardness and endurance limits of steel and decreases the tendency towards creep. It also increases the steel's resistance to corrosion. Vanadium. Vanadium produces a fine grain structure during heat treatment, promotes hardening ability, and increases ductility. Copper. Copper readily combines with many other elements and improves the atmospheric corrosion resistance qualities of the steel. Lead. Lead improves machinability. Manganese. Manganese increases strength and hardness, promotes high impact strength, and offers excellent resistance to wear by abrasion. Tungsten. Tungsten produces a fine grain structure. The alloy retains hardness and strength at high temperatures. Types of non-ferrous engineering materials. Copper. Obtained from copper ore, which is smelted and then further refined by electrolysis. Commonly made into castings, wire, bars, sheets, plates, tubes, etc. The properties which make copper desirable as an engineering material are its high electrical conductivity, high heat conductivity, high corrosion resistance, and high ductility and toughness. In a power plant, it is used primarily for electrical equipment, and as an alloy in the materials used for heat exchanger tubes, valves, and fittings. Copper alloys. Copper alloys are stronger, easier to machine, and have better corrosion resistance. The most commonly used copper alloys are various brasses and bronzes. Brasses and bronzes find use as condenser tubes, piping, valves, fittings, and bearing shells. Brass, an alloy of copper and zinc up to 40%. Frequently, small amounts of other metals such as lead, tin, nickel, aluminum, and manganese are also included in the mixture. Bronze, an alloy of copper and tin, sometimes also containing zinc to ensure non-porous castings, and lead to improve machining qualities. Additions of up to 1% phosphorus produces bronzes or bearing bronzes, which are hard but not abrasive. Bronze is approximately equal to pure copper in its resistance to corrosion. Aluminum. Produced by electrolysis of bauxite ore. Being only 1/3 as heavy as iron or steel, its low density is one of the most valuable properties of aluminum. It is also an important material because of its good conduction of electricity, excellent conduction of heat, and high resistance to corrosion. A disadvantage in its pure form is its low tensile strength. Aluminum is usually alloyed with other materials such as copper, silicon, manganese, zinc, nickel, magnesium, and chromium in order to improve its properties. Aluminum alloys are used for internal combustion engine parts, aircraft parts, tubing, water jackets, etc. White metal. White metal is the name given to alloys made up primarily of lead and tin. It often contains small amounts of other elements such as antimony, bismuth, silver, or zinc. For a power engineer, white metal is chiefly found in bearing materials because of the following properties. Easily melted and cast into the bearing shell. Sufficient strength and ductility not to crack or squeeze out under heavy loads. Soft enough to wear to conform to the shape of the shaft. Good thermal conductivity to carry heat away from the bearing surface. Different combinations of the alloying elements are used to produce white metals suitable for various applications. Babbitt, a common tin-based white metal, is composed of 89% tin, 7.5% lead, and 3.5% copper, and is used for high-speed light load applications. A lead-based white metal is used for slower speeds and heavier loads, and is composed of 10% tin, 15% antimony, and 75% lead. These were my study notes on Power Engineering 4th class, Engineering Materials.